Okay, cool. Thanks for joining. Yeah. I hope you had a great reInvent so far and enjoyed the party, but you still made it here. That's good. Thank you so much. I guess you all know that it's really easy to sell products online, right? So everybody's doing that. Everybody's buying products online. You're probably building an e-commerce application or part of a team. But you might be wondering if there's a better way to engage with users. And also, you might be offering more options, right? People can customize basically everything. Yeah, you can mass customize basically all products. So you need to find a good way to visualize this and to engage with the users. And that's what we're going to talk about. So I'm Christoph Kassen. I'm a solutions architect with AWS. And this is Claudio. He's from MUX. And we're going to talk about 3D configurators. So we'll share what is a 3D configurator anyway. And what kind of technology do you need, or what kind of technology can you use to build such a thing? Then we're going to talk about how you can put this on top of AWS instances. And then we'll share some architecture diagrams for you, how you integrate this into your existing architecture. Because most of you will not be building this from scratch, right? You have an e-commerce application where you sell stuff, so you need to integrate it. And then Claudio will talk about what they've been doing at MUX, and he'll share their learnings, what they learned over the last couple of years building a 3D configurator for their products. So you'll see that as well. We're going to talk a bit deeper, so it's level 400. So if you think this might be too technical or too early, it's fine if you head out. And you should have a basic understanding of 3D visualization. But I guess most of you have played a 3D video game on a gaming console, so you'll know what 3D is and how that works in theory. So let's dive in. What is a 3D configurator, and why do we want to build this? Right? So you might have already seen one if you go to a car manufacturer's website. So if you want to buy a new car, they'll give you all these options, right? You select the color, the wheels, and then they show you the interior as well. And you can spin around the car so you get a good impression of what the car you will buy will look like. You can do the same for fashion. You can customize a handbag. You can customize shoes. You can also do it for furniture. That's what these guys are doing. So that's what we're going to focus on. So if I want to buy this couch for my apartment, I need to get the right size. It needs to fit in my apartment. It needs to be big enough so I can seat all the people I want to sit there. I can choose the material. I can choose the color, all kinds of things that I can customize. And if I can do that as a customer, then it's much easier for me to visualize the final product. And then I'm much more likely to say, OK, this is a good product. This is what I want. And I know what I'll be getting, so I'll just go ahead and buy it. So we get a visualization of the final product, and that makes it just easier for me to go ahead and buy. You want to do this, obviously, with server-side rendering, because you want to control the quality. It needs to be magazine-like quality. It needs to look really, really nice. So you need to be able to control this across all the devices your users might be using. They might be using a very old smartphone, or they might be using a tablet. You still want to have the same quality for your rendered images everywhere. You also want to control the rendering speed. It shouldn't be slow just because the device is slow. So you want to serve the images as fast as possible to your users. Because we all know if the website is slow, people drop out of the e-commerce process, and then you just lose revenue. And you want to control the cost. So you want to have a rendering fleet where you can scale up and down based on the demand. And if people are asleep, you don't need all the rendering power, so you can turn down those instances. So it makes sense to do that on the server side. In terms of rendering technology, we have basically two options we can choose. First off is something called Rasterizer. This is what a 3D game typically uses. It's composing the scene, the animations out of vectors and polygons. And then it's just pushing out millions of these polygons and that's what's up on the screen. It's very, very complex to build this, and that's why people use OpenGL or DirectX to build these game engines, to make it easier for them to apply things like shaders to the polygons to make the image look really nice. And this is also the original use case for GPUs. They have been invented for specifically this type of 3D engine, to speed up all the calculations necessary to create nice 3D images. That was the original use case why they've been invented. The other option we can have is something called ray tracing. Now, this is what you see when you go to a movie and see the latest Disney or Pixar movie, or if you see a blockbuster with all the CGI animations, then it's coming out of a ray tracer. And the way this works is you basically model your 3D scene, so you place your objects in there, you put light in there, and then you place a camera in there. And from this camera, tracers are sent out through the scene, and then they bounce back off the object, and that creates the resulting image. And then you just move the camera around, and that gives you the animation. The biggest advantage is it's photorealistic images we get out of this. It's really hard to tell if this is a photograph or if this is coming out of a ray tracer. So it's very, very good for our use case, because we want to have photorealistic images of our products, so to make them look cool. The calculations necessary, massive, so very slow usually, but we all know GPUs can do much more than just do 3D animations. They can do all kinds of things. We can use them for machine learning, but we can also use them to speed up this ray tracing process. So if the ray tracer is capable of utilizing something like CUDA, then we can offload all the calculations to our GPU, and then we massively speed up the rendering process. So it's fast enough for our use case. So how do you do this on AWS then? So what we offer is we offer GPU instances. We offer the P3 instance family and the G3 instance family. The P3 is based on the Volta architecture. So that's the latest and greatest coming out of NVIDIA. And then there's also the G3 instances. And you'll see in a couple minutes why there's a difference. They're based on the Maxwell architecture. So it's a different microarchitecture inside the GPUs. And then you can just select if you want 1 or up to 8 GPUs or 1 or up to 4 GPUs. And then they have plenty of CPU capacity and plenty of memory in there as well. So these are really, really powerful machines we can use to build this configurator. Another option is that we use something called Elastic GPU. We might not need the full power of these super GPUs. We might just need a bit of GPU power because we have some application, let's say we're not rendering the final picture of the product, but we're trying to render the assembly instructions for our couch. But we want to still have a 3D visualization of the product in there. So we can use the Elastic GPU because that allows us to run a smaller instance. Now we can just run a T2 instance or an M4 and still attach a GPU instance to that. It happens over the network, and it's currently Windows only, and keep that in mind, it only supports OpenGL 4.2. So there's no CUDA acceleration or OpenCL or DirectX at the moment. So you need to make sure that your 3D engine, whatever you pick, is capable of running in OpenGL mode, and then maybe force it to actually utilize that and not fall back to software rendering. Also, as you can see on the picture, the Elastic GPU is attached over the network. So keep that in mind, because it consumes an additional IP address in your VPC subnets. So if you want to run this, make sure your VPC subnets are big enough, because otherwise you run out of IP addresses. To conserve bandwidth, the rendering happens at 25 frames per second maximum. So keep that in mind as well. And you can edit the driver's configuration file and then show a frame counter. So you can see if you're rendering at the 25 frames or if you're significantly below that. Then it might make sense to upgrade to a bigger Elastic GPU. And if you want to check what kind of capabilities they support, there's tools like the CAPS viewer where you can see what kind of capabilities are supported by the driver at the moment. So now that we've seen the options, how do you choose now? So the P3, super good for machine learning and all kinds of simulations, calculations where you really benefit from the huge number of CUDA cores in there. So if you have this type of workload, go for the P3s. If you're running a ray tracer, go for the P3s as well. The G3s, on the other hand, since they're based on a different microarchitecture, they're better suited for 3D visualizations and 3D renderings, or anything that's OpenGL or DirectX. That's supposed to be faster on the G3s based on the GPU in there. And as I said, the Elastic GPUs, if you want to have GPU capabilities in your instance, but it's just a smaller use case where performance is not that critical, and you're just running OpenGL, then it's also a good option to go with the Elastic GPUs, because then you run smaller instances, you save cost, and that's also a good thing, right? So now let's take a look at what do we need to build to integrate this into our web application stack. So we want to build a rendering API that acts as the interface between our renderer and the rest of our application stack. We have an application stack, can be monolithic application, can be a set of microservices where we want to integrate this. Then, of course, we need to decide what kind of rendering technology do we want to use and what kind of software is out there that we can use. We, of course, also want to have a 3D model, right? We need to have something which we can render, and we need a way to change this model so that the configuration changes the user makes are reflected in the model so that we can render the updated images. We also might want to add in some caching, because the user might just press reload accidentally. There is no need to re-render the image over and over again just because of this. So we want to add some caching in there as well. We want to have real-time or near real-time rendering, as I said before, and we want to have really high quality images. So let's take a look at the rendering, what we can use. So for rasterizers, there's, for example, the Unity 3D game engine. It's quite popular, and that's an option you can use. There's also Amazon Lumberyard. It's also a rasterizer. That would be another option to consider for building this. In terms of ray tracers, there's a huge option of commercial options available. There's one from NVIDIA and all kinds of other tools. But there's also Blender, which is an open source project, and they have a renderer called Cycles, which is very good. And I used Cycles to render the image you see here. So I just picked up a model and then just ran that, and that created this image. So then we need to decide how do we pick up the image in the end, right? We can always write it to disk and serve it somehow from there. We might also just want to grab the frame buffer of the operating system and just pull out the images from there. Or if we want, depending on the engine we use, we can also build a native integration so we can directly push out the images back over the HTTP connection to our user. That kind of depends on what technology you pick. Writing to file is probably the easiest. So if you want to just get started with Blender, it's actually pretty easy. You just spin up a GPU instance, for example, and then you can just run Blender from the command line. Yeah? Just provide the model file, where to write the output, and then you need to provide this little Python snippet you see above to ensure that it's actually forced into GPU mode. So that's what I'm doing here. So I'm setting up Cycles to run on the GPU, utilize CUDA, and then I'm setting up the tile size for optimal rendering speed. And that's it. And then you can just go ahead and render the image. You'll get a resulting frame on disk, and then you can serve that back to your users. So the architecture can look like this. Requests come in, and then they'll hit CloudFront, so we can have caching at the edge locations already. We can also use CloudFront to redirect certain requests to pre-rendered images, static assets, these kind of things. So these requests are already really fast. We just have our existing fleet of services, our e-commerce application, probably sitting behind an application load balancer, and most likely within an auto-scaling group, so we can scale up and down depending on traffic. And then what we do is we add our fleet of GPU instances in there, and they host our rendering API as well. So the renderer and the rendering API, we can just host those on the GPU instances. And then we can make calls from our application to our rendering API and get served images. What we can also do is we can put in the network load balancer, because then we're not sending the images back over CloudFront, which would be good because then we have caching already built in. But it might be faster to use something called HTTP2 push, which directly streams the image back to the user. And we can do that if we add in the network load balancer, because that's a TCP level load balancer, and that allows us to do exactly that. But of course, then we need to add in caching in our rendering API, because we lose that capability there. But that's something you can just add to the rendering API. If you say, OK, I'm not that interested in ray tracer, I have a smaller use case, I want to go with the Rasterizer, maybe you want to also use that for batch processing. But for the web architecture, this is simpler then. We still have CloudFront, we want to have the caching. We get that out of the box with CloudFront. We can still serve pre-rendered images. And we just have a fleet of instances, and we attach the Elastic GPU to these instances. And then we just run, for example, Unity on these machines, and then we render the images there. If you're running this, you need to obviously monitor this. So for the GPU instances, the driver comes with a tool called NVIDIA SMI, and you can use that to monitor your GPUs. The Elastic GPUs, they push their metrics to CloudWatch automatically, so you can pick them up there. You can also add custom CloudWatch metrics, so you can just measure the time it takes to render an image within your rendering API and push that to CloudWatch. And then you have additional metrics there to monitor and also to set up your auto-scaling rules on those metrics. And auto-scaling, as usual, always scale up aggressively. Don't add a single instance, add multiple. And then scaling down, always scale down slowly, so you're not overwhelmed by the requests. This is how it looks like if you push custom metric to CloudWatch. This is what happened while I was rendering the image I shared before. So you see all the GPUs in that GPU instance were fully utilized for just the 2 minutes the rendering took, and then they were back idle again. And now I could go ahead and build alarms on this and monitor my fleet of GPU instances. And it's actually pretty easy to do that. It's just a couple lines of code, and since the slides are posted, you can just copy-paste it afterwards. But all I'm doing is I'm just running NVIDIA SMI. I'm querying for the utilization of my GPU and the memory utilization. And then I'm parsing that data. I'm pulling out the instance ID. And then with the 2 last lines, I'm just pushing those metrics to CloudWatch. And then I just set it up to run continuously on that machine, and then I'm good to go. Very easy, but very effective. A couple other things you want to do if you run GPU instances, because the NVIDIA SMI tool is capable of much more. You can disable the auto boost feature these GPUs have. And you want to do that for some obvious reasons. You want to have maximum speed, and you want to have predictable latency in your rendering. So you can just disable that feature. And you can also make sure that the GPUs always run at maximum clock speed. So these are the commands in there. You can persist these settings. But if you're auto-scaling, you want to apply this on every instance creation, obviously. So the last thing I want to give you is, let's call it a circuit breaker. Think of the situation where your marketing team decides to run a TV campaign, or you're featured somewhere. And suddenly a lot of users come to your store and start browsing around. Now, you want to have a way to somehow handle this traffic. The auto-scaling kicks in, but it needs a bit of time. Maybe you also hit the limit of your auto-scaling group, so you would need 20 instances, but you only allow 10. So what we can do is, since we're already sending traffic through CloudFront, we can utilize something called Lambda at the edge. If you know that, it's an edge function, so it's a Lambda function which is called at the edge locations, so very close to the user. And we can integrate this into our architecture. So whenever the request comes in, we can call this Lambda function automatically. And then within this Lambda function, we can do network requests. And that allows us to call a metrics endpoint on our rendering API. And we can expose if we're overloaded, or if we consider our GPU fleet to be overloaded, or if we just say, OK, I don't want to live render this. And we can serve that back to the Lambda function. And then CloudFront will simply rewrite the request. So that's a very good way to automatically handle this, because then in certain situations, you can just serve pre-rendered images to your users. They will not immediately see that, but it gives you time to react, to spin up more instances, or maybe people are just browsing around and won't buy anything at all. So they see a shop, they know about your product, and then they happily leave because they go to the next website anyway. And that's actually pretty easy to do. It's just a couple lines of JavaScript code we need. So all I need is this simple Lambda function. I'm simply calling my metrics endpoint, and here it's just something which returns JSON. Then I just parse this JSON, and I just check if the overloaded flag is set to true. And I can decide freely when I will consider it to be overloaded. So that's something where you can decide on certain rules. And then all I do is simply rewrite the request. This is completely transparent to the user. The user does not see this. So I can either serve a pre-rendered image, send them to a different page, and that's it. It's a very, very good way to handle this automatically. And with that, I'd like to hand over to Claudio, who will now share what Mix has been building.
Thanks. All right, hi everybody. I'm Claudio. I'm the CTO of Mix. Sorry. And we sell furniture, modular furniture that you can customize yourself, and that way you can build your own shelf, wardrobe, couch, and so on. And we do this by offering 3D online configurators that works in real time, and you get a photorealistic representation of what you're building. And because it's modular, it allows you to have a big variety of products that you can build. And since it is modular, we have all the pieces in our warehouse, which allows us to have a very short time lead times, which is not common in the furniture industry. And it also makes our furniture affordable for a premium quality. So let's talk now about the 3D configurators. What I want to present you is our experience so far that we have collected over 3.5 years, more or less, building 3D configurators that are basically generating server-side renderings. We are using ray tracers, as Christoph already mentioned, and everything is on Amazon. And at the end, I will share with you our lessons that we have learned over this time. So when it comes to configurators, you have two major challenges that you are going to face. On one side, you want a high level of interactivity. You want the users to be able to choose every part, and in our case, furniture, highlight sections, change the materials, sizes, and so on. But at the same time, you want to offer to your users a photorealistic representation of what you're selling, and in the case of an e-commerce platform. And and both things, they don't necessarily work perfectly together. You have to either decide for one or the other and find compromises in between. So if you want photorealistic representations, you will have to go with server-side renderings. And if you want a high level of interactivity, you go with a client-side solution, which nowadays is WebGL, which you run in your browser. To give you a feeling what I'm talking about, this is one of our couches that we sell rendered in WebGL. As you can see, it is extremely glossy and looks like some 3D object from a game from the mid-90s. And that's not necessarily something that you want to show to your customers, especially in the industry of furniture. It's a rather expensive product, so you really want to communicate the quality and give the user this, the right look and feeling of what they might be buying. So if you rendered exactly the same image with the same scene, the same 3D geometries and textures, materials, this is what you get from a server-side renderer. It looks much better, especially for fabrics. They are extremely difficult to represent with WebGL. There are a few other situations where when you have very glossy, high reflective surfaces that where you can use WebGL and it's going to look okay. But if you have fabrics where you have different colors and shadings depending on your light settings, that's something that you will probably not be able to manage with WebGL. So when we started the company, we had this challenge. Do we go with high interactivity or photorealism? And we know, or we knew back then that from our customers, potential customers, that the photorealism was a very important aspect of our online product. So we decided to go with server-side renderings. And when we did that 3.5 years ago, more or less, we defined a set of goals of things that we wanted to achieve with such a solution. So we said that every image has to arrive within 2 seconds after any user interaction, so that the user clicks on apply a new, or select a new wood type and apply it to my, I don't know, like a wall of your shelf. In 2 seconds, it has to be there. We wanted to have a progressive stream of images. I'm going to go deeper into that later. But basically, you get on first click a very low quality image that goes that improves over the time. We still wanted to offer a high degree of interactivity. That's absolutely needed to offer a good user experience. Cross-device compatibility, it's also important, especially 3 years ago, 4 years, WebGL was not supported as good as it is now on mobile devices. And it has to be scalable and affordable. At the same time, we were, of course, also aware that server-side renderings, they're not really meant to be, or they're not optimized for real-time applications. They're rather used for interior designers, architects, simulations, where time is not that big of an issue as an application that runs on your browser. Because you just get plain images, PNGs, JPEGs, it's difficult to add interaction to those images. How do you select a leg from your couch if you just have an image and you highlight specifically that leg, for instance? Also, doing server-side renderings, and if you really go into the topic of renderers, the learning curve is steeper than using a common WebGL library such as Babylon.js, Free.js, and so on. And GPU machines are expensive. So you want to make sure that you utilize them in a very efficient way. So when we talk about server-side renderings, we also talk about ray tracers. The ray tracers are a way to simulate in a photorealistic quality images. So the way it works is that you define do you have a pointer? So I cannot see the pointer there. So you define an image over there, and you define the size of the image, and width and height, and for each pixel, you throw a ray through it, and once it collides on your scene with any 3D geometry, or maybe it might not even collide with something, it takes into account all the other geometries and light settings and so on into account, and that's a calculation for that specific pixel. What is the color I need or I should use in that case? And that you do it for every pixel. And it's a very efficient algorithm that runs quite fast and generates extremely good-looking images. So this is something that you can generate server-side. It's showcasing one of our couches and one of our tables that you can configure on the website. And yeah, the stuff we were consuming while we were building this. So let's talk now about AWS GPUs and how we put this together. When it comes to server-side renderings, it's always a matter between speed and making it scalable and affordable. GPU machines are among the most expensive one on Amazon. Right now, you can choose or take a P3 machine with a Tesla architecture, V100. Excellent machine, extremely fast, but it's gonna cost around $25 an hour. And you need at least 2 of them because you don't want to have a single point of failure, so you want to be flexible on that. So that's like $35K a month for just 2 servers. So you want to make sure that you distribute and load balance your users as good as possible and that you use those resources in a very effective manner. And that has been a long journey for us. And our first AWS infrastructure that we came up with looked like this. So on the left side, we have CloudFront, Lambda, and S3, where we run our single-page application. It's built on React. At the very beginning, we didn't have Lambda. That came later. Then in the center, we have our microservice architecture. It's just a set of different APIs that are running on Node.js. And then on the very right, we have our auto-scaling group with our rendering farm. And that's the interesting part for us. So we're going to focus on that part of the architecture. And I will show you how it evolved over time and the challenges we were facing during this time. So before going into the different infrastructures, this is how our streaming of images used to work. So when we started, you only had ELBs. And as you probably know, ELBs don't support WebSocket. So that makes it more difficult to stream intermediate images. And the way ray tracing works is that you generate many images of low quality and you sample them together to get the final image that looks good and photorealistic. So what we were doing is that the first orange line is a request to get a specific rendering. And then we open a long polling connection to our servers to retrieve all those little images in between. So you have a progressive stream of images. So while you're rendering the image, we request those intermediate images. Once it gets back, that's the dashed purple line. We display that on the client, and we send another request to get the next one, and so on and so on, until you get the final image, which we cache in between, and then, of course, you stop requesting in intermediate images. So this is how our rendering flow looked at the very beginning. We had an ELB in front of Varnish. We were using Varnish as a layer 7 router. It was also caching our images in memory and was working yeah, basically there was a service running on it to do service discovery, and depending on the type of the URL, dispatching the different requests. Then we had a rendering API. Those were just normal EC2 machines running a Node.js application, and then go through an RELB to the rendering farm, which was inside an auto-scaling group. At that time, when we started, you only had G2 machines. I said this was 3.5 years ago. This infrastructure had a major problem, or that at least we were facing, and it was chasing us for quite some time. It is difficult to distribute the load efficiently among all the machines. The way the ELB is working is just doing round-robin load balancing. It works extremely good if you have a high level of traffic, but not if you are around 100 users simultaneously doing some rendering. So we ended up many times with GPU machines being idle where others were crashing because they were rendering too many images in parallel. And so once we realized that and we tried to find solutions for that, we came with the next version where we basically simplified our infrastructure, and we placed all those Node.js applications inside of each of our GPU machines. That was way more efficient because each web app or API was just taking care of a single GPU machine. And still, it was not perfect. What we realized is that the NVIDIA SMI, it's a great way to monitor the load of your GPUs, but it is extremely greedy. So the way it works is it tries to use every available resource to generate your image as quick as possible, which is something you want. But that means it's going to use all the GPUs, GPU cores, if the settings are the right ones. It's also going to use all the CPU cores that are available on the machine. And that's just one line in the settings, which gives you something between 10 and 20% speed boost. And so if you look at the metrics on CloudWatch, everything is at 100%, sometimes even more, or it's a 0%, or close to 0. So it makes it really difficult to use that as a metric to know when do you want to scale up and scale down. It's quite Boolean. So what we did then is we came up with, we call it a pool of sessions. So for each machine, we decide that, and we were doing some benchmarks on those machines, that if you have 4 or 5 renderings simultaneously running, that was okay for the machine. And then if you go beyond that, there's a high chance that your application is going to crash, or the user experience that you are going to offer is going to be very poor. At the same time, we also realized that we have different types of images that you want to generate. On one side, we have the configurators, where you want to get the image as quick as possible in a photorealistic quality. But then you have also other kind of images, at least in our case. So when you create a new bookshelf, for instance, and you hit the Save Design button, you will get that design sent to you via email, for instance. And that's going to be rendered in a higher quality, and it's also going to be a bigger image. But in that case, you don't need it as quick as possible. If it takes 1 minute until you get your email, that's totally fine. And we have a bunch of images that follow that pattern. So that led us to our next version of the infrastructure, where we split the load depending on what kind of image do you want to generate. So on the upper part, you have the rendering API, and that one is for the configurators, so as quick as possible, less than 2 seconds, as mentioned. And since all the GPU machines on Amazon are using NVIDIA cards, we are using IRT for that. That's interactive ray tracing. It's a rendering engine from NVIDIA. And then on the bottom, we have those images that if they take 1 minute, 2 minutes, it's not an issue. So those we were rendering with iRay. It's a better quality image. It's more photorealistic. That's also a rendering engine from NVIDIA. And we were adding all those requests to an SQS queue and just consuming the jobs from that queue. That was also the time around when the P2 machines came in, giving us a great boost in terms of speed. But we still had this issue of not being extremely efficient by load balancing our traffic. We always had this problem of having a few machines idling around and others being overused and doing many renderings at the same time. So we added a new version of our infrastructure. And this is actually pretty close to what we have right now on our website. So once the ALB came in, we finally got support for WebSocket, and we could get rid of the long polling strategy that we had at the beginning. And you can also see a small speed improvement with that. So what we are doing now is that we have an image broker, which is at the top. We call it the image broker. It's a bump server. That's a sub-protocol from WebSocket. When it's just a pub-sub messaging pattern. So you subscribe to a certain image, and which is unique because of the hash that defines a design. So you can, by that, listen to every time a new image is ready to be used, and then you have your progressive streaming of images. Sorry. Then we also add a queue inside of every machine. That's that purple squares inside our auto-scaling group. Because we were trying to fight this situation of having idle machines and a few overused. So what we realized once the P2 machines came in and running some benchmarks is that running renderings on just one GPU instead of using all the available resources was at the end more efficient than using them all, and then if a new request comes in, we just put it on top, and then we were actually rendering at the same time many images. For the first user, that user won't really notice a difference, but the second user, the third, and so on, they will pay a penalty for being on this queue of running images or generating images in parallel. So this allowed us to simplify even more our architecture. What we were doing before is that we had a sticky connection to the server, because when you initialize your scene, you might want to load in memory all the textures and materials that you have, the light settings for your scene, and there are a few things in this 3D world that don't change. For instance, the floor, and on top of that, in our case, you put furniture. And that was forcing us that on every subsequent request, you were hitting the same machine, and the same GPU machine. And because of that, and having a high load traffic, it's difficult to manage the sessions in an efficient way. So once the more powerful P2 machines came in with more cores and just being much faster than the G2 machines, we were just running every rendering on one single GPU. And then having this queue, or job queue for each machine, And we were also using that as a metric for CloudWatch to decide whether we want to scale up and down. And that was way more, or it is way more efficient than using the NVIDIA SMI. We just look at for how long a job has been in the queue, and based on that, we decide whether we scale up or down. The lower part stayed the same. Those are those kind of asynchronous images that you generate for marketing purposes, and you just consume the jobs from your SQS queue. I don't know if you know this at the beginning, but I said that we had varnish in front of all of our machines and doing the routing and caching and so on. Once AWS released Lambda at the edge, we were also able to get rid of varnish. So less moving parts, and yeah, we basically use CloudFront as a caching layer, which is also extremely nice. And you keep the logic inside of a Lambda function. Our stack is based on JavaScript, so you can just run JavaScript on Lambda functions, which is great as well. So no need anymore for varnish at that point. And this is what we're working right now on. So it's even more simple than our current infrastructure. What we realize is that after using existing rendering solutions, and in our case, iRay and IRT from NVIDIA, you reach a point where there are no more fine-tunings in the configurations to get faster renderings. At the beginning, there are many things that you can tweak, and you will see a high difference, a big difference in terms of speed and quality. But at the end, you follow the 80-20 rule. So you reach a point where you spend a lot of time for the last 20% of improvements. So we decided that we will build our own rendering engine based on open projects from NVIDIA, since AWS offers NVIDIA graphic cards. And what we see now, and we call it Mixed Nice, is that we have a speed improvement from 5x, 7x compared to our current solution. Because it's tailored just for our use case. It's a very simple scene. You don't have many objects on it. So we were able to kick out everything that it's not needed for us and just focus on that single furniture that we want to render. AWS introduced the network load balancer, which gives support for HTTP2 push for streaming of images. We had to remove CloudFront for now, because sadly you have a limit in the size of your query. So query strings cannot exceed, not sure what's the max length, but basically we send over query strings the data structure that represents a specific furniture, and that's just longer than what's supported. So we're using Elastic Cache, Redis, to cache the images that we generate, and we move from get request to post, so we don't have this limitation. That's something that's going to change for sure soon. And then we go back to get at CloudFront, and we can get rid of Redis. So as I said, this is something we're working on, and we hope to launch it soon and see this amazing improvement and speed and also quality of the images. And so what have we learned over this process in the past 3.5 years? Aim for the best possible hardware. We realized that Amazon is constantly releasing new type of machines. I said at the beginning, you had the G2 machines, then P2 came out, then G3, now you have P3 machines. always test them, see what works best for you. And in our case, right now, the P3 machines are the best hardware to run our renderings, better than the G3. But that just depends on the renderer that you might be using. So test them all, benchmark, and see what works good for you, and also what makes sense in terms of pricing. Don't be afraid to step deep into rendering topics. So when we started, we tried to use solutions out of the box and just fine-tuning a bit and see what we get out of that. And it was okay to have a running prototype and a proof of concept. But when you really want to get out every possible millisecond to improve the quality and the speed of your renderings, you really have to go deep into the topic and develop an understanding of how renderings in general work. So what is ray tracing? How does it work, and so on? How do you actually trigger renderings on a GPU level? What does it mean? Always reevaluate your infrastructure. As I just showed you, we went through many versions of our infrastructure on AWS. And there were actually a few steps in between. It just would have been too long to show everything. But since Amazon has a huge amount of services, and there are always new services coming in, there's always something that can be improved. And there are always 100 ways to get to the same result. So at the beginning, just to have something up and running, because there is a business that you want to run and sell furniture, in our case. Getting to that point is totally valid, but once you are live and everything is on production, reevaluate what you have. Are there better ways to get to the same result in a faster way, cheaper way, more scalable? And there are just tons of services that will help you on that. Keep most of the energy on the renderer. What I mentioned before, like this 80-20 rule, it also applies to the hardware aspect. Better machines, better graphic cards, they do give you a nice boost in terms of performance, but at the end, you will get the most out of by fine-tuning and understanding how the rendering engine is working and tweaking it to just fulfill your needs, more than just using bigger and faster machines. At least for us, that's how it works. And don't just stick to one technology. Basically, it refers to all the previous points. Always reevaluate your infrastructure, look for better solutions, other services. Because as I said, there are so many ways to get to the same result. But as also mentioned, GPU machines are expensive. So you want to make sure that you use them in a very efficient way, that you load balance your traffic very efficiently, and that you scale up and down accordingly to your traffic. Thank you very much.